In this video, we want to use our knowledge of transformations to graph this function. K of x is equal to 1/3 times the absolute value of x plus 3 minus 4. So we always want to start by identifying the parent function. So imagine taking away the 1/3 in front and the plus 3 inside of the absolute value and the minus 4, which are all going to create transformations. If we strip those values away, what's left is going to be our parent function. So our parent function will be y equals the absolute value of x. Now the ultimate goal is to graph this function without using our calculator or without using Desmos or any sort of technology. So in the beginning, if you do not remember what the absolute value of x graph looks like, then I encourage you to go ahead and make a table. And remember, for the domain, the values that we're allowed to substitute in for x, we have no restrictions. So we can substitute in negative values, 0, as well as positive values. So the absolute value of -2 is +2, the absolute value of -1 is 1, and so on. We know that we're always going to get out a positive y value or a positive output for this parent function. And if you graph the points in our table, -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2, we start to see that we get this V shape. And that is the basic shape of the absolute value of x function. So you can go ahead and continue plotting some additional points, and then using a straight edge, we want to be as accurate as possible, to go ahead and graph in your V. And this is our parent function, the absolute value of x. So we expect our graph of k of x to have a similar shape, but we're going to use our transformations to see how the graph has changed. So I see 3 values. Again, we have the 1/3 out in front. We have the +3 inside of the absolute value. And then we have the -4 outside the absolute value. And all 3 of those numbers are going to create a transformation. So we're going to go ahead and identify the 3 transformations. Now, the way I approach transformations, I always tell my students to just shift last. So if you have any sort of a shift, I prefer to do that at the very, very end. Now, some instructors and some textbooks will tell you to abide by order of operations, and that certainly works as well. If you were to abide by the order of operations, you would do what's inside the absolute value first, because that's a grouping symbol. So in this case, you would deal with the +3 first. Then you would address the 1/3 out in front, and then you would address the -4 last. That's how a lot of textbooks present this. But over the years, I have found that my students have better luck and make fewer mistakes if they just choose to shift last. So that is my personal preference, just from years of experience and seeing a lot of students make a lot of different mistakes. So in this case, we have the x plus 3, and that +3 is with the x, so it's going to impact the graph horizontally. It's going to move it to the left or right. And we know it's going to move left 3 because it's a +3. So let me explain that. If you were to ask yourself, what value could you plug in for x that would cause the entire absolute value to become a 0, we would plug in a -3. And so that -3, think of it as basically moving the original vertex of the graph, which used to be at 0, 0, and it's going to move it to the left to -3. So that's a shift left 3. But again, I'm going to shift last, so I'm going to go ahead and put left 3 as my second step, because I also have this -4 on the outside of the absolute value, which is going to be a shift down 4. Now, I'm assuming if you're watching this video, you've already done some of our basic transformations, so I'm not going into super deep detail as to why these shift the way they do, because that's been addressed in earlier examples. So we have a shift left 3 and down 4. And again, I'm listing those last as steps 2 and 3 because we're going to shift last. Then in front, we have this 1/3, and we have to remember the 1/3 is being multiplied by that parent function. So if you think of 1/3 getting multiplied by the parent function, and if I were to just call that parent function f of x, Imagine it could be any generic parent function, calling it f. And if you think of f of x as y, we're basically multiplying my y values by 1/3. Now that's going to create a vertical compression. And remember, it's a vertical compression because our y values are all going to be 1/3 as big. In other words, if you look at our table, it's like we're multiplying all of our y values by 1/3. So I'm going to do that vertical compression first. We're multiplying all of these y values by 1/3, and we're going to get our new y values. Notice the x values don't change. So 2 times 1/3 is going to be 2/3. So I'm going to plot the new point, which is -2 for x and 2/3 for y. So that's left 2 and then up 2/3. So you'll just estimate 2/3. Then we have 1 times 1/3, which would just be 1/3. So now I have -1 for x and 1/3 for y, just barely above the x-axis. 0 times 1/3 is still 0, so the vertex doesn't change. 1 times 1/3 is 1/3, so that's 1 comma 1/3. And 2 times 1/3 is 2/3. So initially, I have those 5 points. Now that may not be enough for you to clearly see the graph, so I would encourage us actually to go a little further. Let's go to x equals 3. Now again, on the parent function, y equals absolute value of x, when we put in 3, the absolute value of 3 is just 3. Now when we do the compression, we're multiplying 3 times 1/3, which will give us a y value, a new y value of 1. So we're plotting x equals 3 and y equals 1. And you can see that's going to give us a good point, a point with nice whole number values for x and y. Now we could have also done -3. The absolute value of -3 is 3. And notice when you do the stretch there and you multiply by 1/3, my output is 1 again. So when x equals -3, my y value is +1. So rather than doing 4 or 5, if you're thinking about other good values, 6 would be a good value because the absolute value of 6 is 6. So then when you do your compression and multiply by 1/3, 6 times 1/3 will be 2. So if you plot 6, 2, here's another good point on the graph. And now you know that -6 would act the same way. Because if we do the absolute value of -6, we would get +6. And then multiplying by that compression of 1/3, we see we'd end up with +2 as well. So at -6, we're up at +2. This gives us enough information to go ahead and graph the result. So it's still going to be a V-shaped graph, but the graph has been vertically compressed because of the multiplication by 1/3. So this would be y is equal to 1/3 times the absolute value of x. We've only done the compression. Now before we move on, you may notice something about each of these sides of the V. And I want you to take a look at the slope. Starting at the origin, notice that from 0, 0, we travel up 1 and right 3 to get to the next good whole number point on the V, and we travel up 1 and right 3 again. So that's basically like saying the slope of the right-hand side is 1/3. And likewise, if you were to go the other direction from the origin, up 1, left 3, up 1, left 3, you can see the slope of the other side is -1/3. And once you notice that once or twice, that actually can be used as sort of a shortcut to help you graph absolute value graphs. Because when you see a number out in front being multiplied by the absolute value, that's creating the vertical stretch or compression, depending on how large the number is. In this case, a compression. We could actually use that compression as our slope, and knowing that the right-hand side has a slope of 1/3 and the left-hand side has a slope of -1/3 would help you graph the vertical compression in a much faster way rather than making a long table. So you can pick the method that works best for you. Finally, we're going to take our graph and move it left 3 as well as down 4. And you can probably do both of those shifts at the same time. So let's start with the leftmost point here that we have at -6, +2. We're going to travel left 3 and down 4. So just count left 3, down 4, and you should land at -9, -2. Then taking the next point, which is at -3, 1, we travel left 3, down 4. The vertex was at 0, 0, but it's going to go left 3 and down 4. So that means the new vertex is here at -3, -4. And then the last 2 points, the one at 3, 1, we go left 3, down 4. And then finally this point at 6, 2, we count left 3, down 4 again. And now we have 5 good points. And you can draw in your V. That has been vertically compressed and shifted left 3, down 4. Now I'm going to label my final graph here K of X because that was the name of the function that was given. And then let's also talk about checking this. So if we had our calculators, we could certainly check with our calculator or with Desmos, or you can check by just picking a point on your V. Now, I don't recommend picking the vertex. I wouldn't pick the vertex point because remember the vertex point did not change when we vertically compressed the graph. It only changed because of the shifting. So don't pick the vertex, but pick one of the other 4 points that we have on our graph. So for example, I'm going to choose this point here, which appears to be at 3, -2, and I'm going to check to be sure I did this correctly by substituting in 3 for x. So in other words, I'm going to substitute 3 into my function. That would be k of 3, which would be 1/3 absolute value of 3 plus 3 minus 4. And I'm just verifying that I will get a y value of -2. So we have the absolute value of 6, which will give us 1/3 times 6 minus 4. And then 1/3 times 6 is 2, and 2 minus 4 indeed is -2, which is exactly what we wanted to get out for our y value. So that's a quick way of checking to be sure that we did these transformations correctly. And lastly, we'll do the domain, which is all the possible x values from left to right. Remember that the arrows indicate the graph continues on forever. So my domain would be all real numbers, or you can write x as an element of the interval from -infinity to +infinity. You don't have to write this x as an element symbol, but it is a useful way of showing that the interval that follows is just the x values. And then the range will be the outputs, the y values from lowest to highest. And the lowest point on our graph is that vertex, and the y value there is -4. So these are y values. And we'll do a bracket on -4 because that point is included on the graph. And then the arrows indicate that the graph goes up forever. So that would be from -4 to infinity, a bracket on -4 and a parenthesis on infinity.